Okay, class, welcome back. Today we are doing our second lesson on work and energy. We're going to be concentrating on the work-energy theorem. So far we've talked about work, and that's when you apply a force that moves something, and we said that the force, let's see, let me just try playing with the thing here. So we say the work equals the force times the cosine of the angle times the distance moved s. So that's our basic work equation. Well, it turns out that when you move something with a force, you're adding something to that force that we call energy. And just like work in physics is not exactly the same as work in normal language, energy in physics is also a very specific thing. It's basically a record-keeping system that turns out to make so many problems much easier to solve. It's this strange quantity, and this quantity is increased when you do work. As a matter of fact, oftentimes you see the definition of energy. I'll just write here what you'll see as the definition of energy. Energy is the ability to do work. Okay, that's your standard energy definition. It's kind of funny because, in fact, it seems like energy comes from work, not the other way around. But in fact, if something has energy, then it can do work. And the energy we're going to talk about first is called kinetic energy. Okay, let's see, we'll get back here. Kinetic energy. And just like we talked about kinetic friction is the friction when something is moving, kinetic energy is the energy of an object that is moving. Don't forget, you can always pause if you want to take notes, because you are playing this back. At least that's the intention eventually when we get to the point where we're really doing a flipped classroom. Okay, so kinetic energy, well, as you might imagine, the faster something's moving, the more kinetic energy it has. Turns out also the more mass it has, the more kinetic energy it has. And the actual equation for kinetic energy is equal to 1/2 mv squared. That's how we calculate kinetic energy. Well, okay, so it turns out that the work done, or I should say the net work, the sum of the work done, is equal to the change in kinetic energy. So we could say that work equals kinetic energy final minus kinetic energy initial, right? Or work equals delta kinetic energy. See if we can handle that. Not bad. So that's basically what this section is about. Not too bad. So you basically, you can figure out work because you have your work equation right here. Kind of a crazy thing there, but okay. And you can calculate energy because you have your kinetic energy equation right here. And then you know that you can look at your initial kinetic energy and your final kinetic energy in your work, and it's your typical idea where you'll have some problem where you know the equation and some things are given, some things are not, and all you have to do is find the unknown. Okay, so let's see, I'm going to try a problem. Let me add a new page, and then I'm going to go back to my old page. I'm going to grab a couple things. Okay, I'm going to grab that. equation there and copy it. Go to my new page. I'm going to, you know what? I'm going to pause first so I can find my recorder. That's not it. Is that it? I think that's it. There it is. I'm going to pause. Okay, now we're going again. I paused and you can see I copied and pasted. Very clever, eh? Okay, so I want you to go to page 165 and we're going to look at example 4. So if you need to, you can always pause the video and go find the problem. Now, let's look at this problem together. The Deep Space, I assume you're back. The Deep Space 1, as a probe, was launched October 21st, and it used a type of engine called an ion propulsion engine. The ion propulsion drive generated only a weak force, or thrust, but could do so for long periods of time using only small amounts of fuel. Suppose the probe, which has a mass of 474 kilograms, okay, so we got mass equals 474 kilograms, is traveling with an initial speed of 275 meters per second. Okay, V initial equals 275 meters per second. Okay. No forces act on it except this one force from the thrust engine, which is 5.76 times 10 to the negative 2 newtons. So force equals 5.60 times 10 to the negative 2 newtons. Nice. Okay, that's the thrust from the engine. This external force is directed parallel to the displacement, S, so we don't have to worry about the cosine, which has a magnitude of 2.42 times 10 to the 9th meters. Okay, so S equals 2.42 times 10 to the 9th meters. All right. Determine the final speed of the probe, assuming that its mass remains nearly constant. Okay, so first of all, let's use some of our equations here. We've got work equals force cosine theta times S. Theta is 0, which means the cosine of 0, let's see, yeah, theta is 0, cosine of 0 is 0. Is that right? I believe so. No, cosine of 0 is 1, of course. So this is work equals force times 1 times distance. Okay, so let's see what we have for work here. Work is going to equal 5.60 times 10 to the negative 2 times 1 times 2.42 times 10 to the 9th. So I'm going to put that in my calculator, and you should get out your calculator and try it also. Okay, so we have 5.6, and then second, the little double E, and then the negative symbol, 2, times 2.42, the little double blue E, 9, and I get, let's see, equals, let me see, 135520000, and of course joules. So you can see that it was a very small force, but it was for a very long period of time, and so you actually ended up with quite a lot of energy. I got to get rid of that that arrow thing. This is the one I'm looking for. 1, 2, 3, 1, 2, 3. Maybe make a slightly thicker line. let's see, what is that? That's 135,520,000 joules. Okay, that's our work. So that's got to be our change in kinetic energy. And what are they asking us for again? Let's determine the final speed. So let me just write that down so I can keep track of it. V final equals question mark. Okay, that's what we're trying to find out. So let's see. Kinetic energy. Oh, you know what? I'm going to go back to this one. Get rid of that thing. Kinetic energy final is going to equal 1/2 times, oh geez, I'm going to try this one more time. Sorry guys.
Please pardon the interruption. Follow students with front office, please.
Oh, I should stop this thing, right?
Ruzo.
Okay, we're back. Now, so let's see, as I was saying, we want to know what the work is. Let's find what the kinetic energy final is. So we have K E final equals 1/2 multiplied by 474 times V final squared. Right, that's 1/2 mv squared. And kinetic energy initial equals 1/2 times 474 times V initial, which is, times 275 squared. So let's see, we can get our calculators, and that is going to be 0.5 times 474 times 275 squared. All right, so that is equal to 179,23125 joules. Just like work, energy is in units of joules. Let's see what we've got here. 17,923,125 joules. Okay, so that's our initial energy. We did this much work, so the final energy should be the initial energy plus the work done. So let's see what we have here. Let's see, I'm going to move this down, see if I can make a little more room. Where do I put my mover downer? There it is. Okay, so what I'm going to do is if I can do this, 1, 3, 5, 5, 2, 0, 0, 0, 0, plus 1, 7, 9, 2, 3, 1, 2, 5. And I'm going to put that into my calculator. I've already got the 17923,125 in my calculator. I'm just going to add 13552 0, 0, 0, 0, and there's my answer. So let's see, that is equal to 153,443,125. Is that what you got? Okay, so that is equal to what? That is going to be our final kinetic energy. See, this here was kinetic energy initial, and this here is work. So this here is kinetic energy final. kinetic energy initial, plus work gives kinetic energy final. So that has to equal 1/2 mv final squared. Okay, so that's going to be 1/2 times 474 kilograms times v final squared. So if we take, now I'm going to get a new page. So I'm going to pause and move over what I need to move over onto a new page. If I can just figure out which tool it is. It is this tool. Pause. Okay, we're back. So now if we want to solve for v, we've got to get this 1/2 and this 474 on the other side. So if we multiply by 2 and divide by 474, we should be all set. Okay, so in other words, if I take 1, 5, 3, 4, 4, 3, 1, 2, 5 times 2 divided by 474, that should equal the final squared. Okay, so that means that the final equals the square root of 2 times 1, 5, 3, 4, 4, 3, 1, 2, 5 over 474. And let me do my calculator and see what that is. Let's see. 2 times 1, 5, 3, 4, 4, 3, 1, 2, 5 divided by 474. Okay, and now I'm going to take the square root of my answer. All right, so this is approximately equal to, and then we should look at the numbers in the beginning. It looks like 3 significant digits. So it looks like about 805 equals 805 meters per second. Let's see what they got. Yep, same answer. So there's our answer, 805 meters per second. And so what happened? It started out, a problem so long ago now, 275 to 805. So it speeded up quite a bit with that small amount of force over a long period of time. Let me see if I can pause this while they're talking. Okay, why don't you take whatever notes you need to take, look over this if you're not sure about the algebra. I sort of didn't write it in here, but you can sort of see what happened. When I multiplied by 2, that canceled this 1/2. When I divided by 474, that canceled that 474. That gave us VF squared. To get VF, we just took the square root of all that. So now, I'm going to make up a problem for you to do. So let me go to a new page. You've got your notes if you need them. You can pause me if you need time to write them down. So let's see. I'm going to just use my writing tool here, and I'm going to try to write this up. Okay, so a 400 kilogram motorboat. See how well this thing catches this. Is initially traveling at 1 meter per second. The motor has a, hold on a minute, someone's at the door. Okay, welcome back. It's actually the next day, and we're going to finish this up. So I was in the middle of giving you a problem to work on. A 400 kilogram motorboat is initially traveling at 1 meter per second. The motor has a thrust
That's how it pushes, of 3,000 newtons. Okay, hold on a minute. Get back in the swing of things here. Okay, let's see. The water resistance is 500 newtons. The rest of that, okay. The water resistance is 500 newtons. Pardon me, this craziness here. Okay, let's see. How fast will the boat be moving after it has moved 10 meters? See what that looks like. Not bad. How fast will the boat be moving after it has moved 10 meters? Okay, so here you've got work energy theorem plus a little kinematic equation. So why don't you go ahead, I'll figure out how to pause this thing and work on this problem, and when I come back, I'll solve it for you. Okay, bye. Okay, so let's see what we need to solve this. We need that work equals kinetic energy final minus kinetic, kinetic energy initial. See what that is. Close enough. Okay, so let's see. Work equals force times distance if they're in the same direction. So let's see. We know that the force is the thrust, 3,000 newtons. The distance is 10 meters. So that means work equals 3,000 times 10. Work equals 30,000 joules. All right. So now let's see. Kinetic energy initial equals 1/2 mv initial squared. So that's going to be equal to, let's see, our m is 400, our v initial is 1, right? So that's equal to 1/2 times 400 times 1 squared. Which should be equal to 200 joules. So that's our kinetic energy initial. Let's see now. So that means that 30,000 joules equals kinetic energy final minus 200 joules. Okay. 30,000 joules equals kinetic energy final minus 200 joules. So that means that kinetic energy final must equal 30,200 joules. So now that's got to be equal to 1/2 times m, which is 400, times v final squared. So let's see, 30,200. To solve that, we're going to have to multiply both sides by 2, divide both sides by 400. So we've got that v final squared is going to equal 2 times 30,200 divided by 400. So v final equals the square root of 2 times 30,200 over 400. Make a little room here. So then, if we put the calculator, let's see. 2 times 30200 divided by 400, square root of the answer. It looks like about, see if I look at my significant digits, I'll call it 12. Okay, so we're saying that that equals 12 meters per second. So that's our answer. I guess I didn't need a kinematic equation after all. Okay, so basically what we said was that we started out on 1 meter per second, and we pushed on it with a thrust of 3,000 newtons against a resistance of 500 newtons. So it's kind of like, oh, I forgot the 500 newtons. Right. So everywhere where I have a 3,000 here, I should have a 2,500, right? Because that's how many, that's really the net force. Forgot about that. Okay, so let's go back. Or should I do it all over again? No, I'll go back. I'll fix my. Okay, so this here should be 2,500. Okay. That means that this one here should be 2,500 plus one more zero because we multiplied by 10. Okay, so that means that this one here is the same way. Two 500 plus one more zero. Okay, now we add 200 to that, and we're going to get 25200. We'll go there, that's right there. Okay, and let me copy that one, and then paste. Okay, got another one. I'm going to put it right around there. Okay, and cross this one out. And let's do paste one more time. Paste some. Where did I get that paste? Paste one more time. There we go. Try that again. Insert. There's one. Okay, that one is going to go right here instead of that. What kind of line do we have? Good. Arrow. That should be fine. Thickness. Let's go a little thinner. Okay, so that's going to go to there. And let me just cross this out. And try my calculator one more time. Okay, I got 2 times 25200. Okay, divided by 400. Second square root, second answer. Now we got 11 instead of 12. Okay, so this should have been 11 meters per second. I don't like where that 11 came out. Let me try that again. 1 meters per second. What do we get here? Nope. 1 meters per second. Jeez. 1 meters per second. All right. Get rid of some of this garbage. Delete that. I'm going to get rid of that one right there. Yep. Okay, delete that. And this one's going to go right there. And we don't really need that thing. Okay, 11 meters per second. That's our answer. I'm sticking with it. Okay, did you get anything like that, or did I make another mistake? Let's assume for now that I didn't. And now we're going to move on to example 5, which looks like it is on page 166. Okay, so let's see. Page 166, example 5. Okay, oh my God. Try this one instead. Page 166. Example 5. So you're all getting your books, you're all finding that spot while I mess around with this thing? Okay. Let's see what we have here. A skier's speed, oh, here we go. A 58 kilogram skier is coasting down a 25-degree slope. Let me pause this for the announcement. Whoops. Okay, well, it's gone. You can see I drew a little diagram of this situation, but I'll still read it through. A 58 kilogram, okay, mass is 58 kilograms, skier is coasting down a 25-degree slope, okay, near the top of the slope. Her speed is 3.6 meters per second, so that's the initial velocity. She accelerates down the slope because of a gravitational force. So we got an mg pushing her down. Even though a kinetic frictional force of 71 newtons opposes her motion, pushes backwards. ignoring air resistance, determine the speed at the point that is displaced 57 meters down. Okay, distance 57 meters. So if we think about this problem in terms of what we've been learning so far, we know that if we know force, the net force, and distance, we can find work. And work is just final kinetic energy minus initial kinetic energy. So really the only trick here is that we need to find the force. We know there's 71 newtons going backward, but how many newtons are going forward due to gravity? So let's see what we can do here. I've made a dot here so that I could do a little free body diagram. By the way, feel free to pause this if you need to take some notes. My phone's ringing. Let me just check. I didn't get it in time. Anyway, let's see. So it's really all about finding that force. So let me see what's going on here. If we did a free body diagram, I'm going to, I think I'm going to make a line, a dotted line for my axes. I'm going to have an axis that goes like this. That's really my x-axis, okay? And so we know that we've got a force, okay? It's going to be a solid line, an arrow, I'll make it blue, coming straight down. That's our mg, something like that, okay? So that's mg. So that's going to be mg approximately equal to 580 newtons because it's 58 kilograms times 10 meters per second squared. So the real trick is to figure out the component of that force that's going down the hill. So let me take, say, red. Oops, I'm going to make a line. Red. And maybe a little thinner. Okay. So there is one component of that force going this way. And then there's another component going this way. And you can kind of see that the 25-degree angle is really this angle right here. Okay? So the component of the force that is opposing the friction and pushing the skier downhill is going to be 580 sine 25, because this is the opposite. When you have the opposite, you use the sine. When you have the adjacent, you use the cosine. So our, I'll call it our sum of the forces in the x direction are going to be 580 sine 25 minus 71. It made it a cosine. I'm going to try that. I'm going to pause it and fix it. Okay, I fixed it behind the scenes. Now I'll get up my calculator. 580 sine 25 minus 71. So we're talking about 174 newtons. 174 newtons. Okay, that was the hard part. The rest of the problem really shouldn't be too bad, right? We're going to have to find the initial kinetic energy and the final kinetic energy. The initial kinetic energy, we have everything we need. It's 1/2 mv squared. There's our m, 58. There's our v, 3.6. So, kinetic energy initial equals 1/2 times 58 times 3.6 squared. Okay? So we should be able to calculate that. Get up my calculator one more time. 0.5 times 58 times 3.6 squared. That's about 376 joules. Okay. Equals 376 joules. Okay, now our kinetic energy final is going to be 1/2 mv final squared. What's the question actually asking us? Determine her speed at the point she's displaced. So we're trying to find v final. Let me write that here. V final equals question mark. That's what we're trying to find. And kinetic energy final is 1/2 times 58 times v final squared. So let's see now. Let me see if I can make a little bit of space here. We know that work is kinetic energy final minus kinetic energy initial, and work is force times distance. So that's going to be, let's see if we can write all this out. Work is force times distance, or F dot S, sometimes we use it. Okay, so that's going to be equal to 174 newtons times 57 meters. All right, let's see, 174 times 57, I'll call it 9,900. 9,900 joules. So that's got to equal this minus this, kinetic energy final minus kinetic energy initial. Now, 58 times 1/2, 58 times 0.5, that's 29. So let me simplify this first. So I can say that kinetic energy final is going to equal 29 V final squared. Okay. So that means that this here is going to equal 29 V final squared minus 376, which is our initial kinetic energy. So this, just so you see what these things are, okay, this is KE final. Whoops, let me try that one more time. Okay, we've got KE final minus KE initial, and this one here is work. So this one is KE final, and this is KE initial, and this is work. So work equals kinetic energy final minus kinetic energy initial. Okay, so if I add 376 to both sides, that's 9,900 plus 376 equals 1,000, I'll call it 1,300. All this rounding is probably going to make my answer way different than theirs, but that's okay. So we've got 1,000, oops. I mean 10,300. Okay, 10,300 equals 29 V final squared. Divide both sides by 29. Now I've got like 354 equals V final squared. Three, 5, 4 equals V final squared. Oops, it doesn't like putting things. I'm going to have to move up here. I'm sorry. Okay, so V final equals the square root of 354 equals second square root. A lot of times what I'm doing is I have the number actually with all the decimals in my calculator, so I'm using the long version of the number, and I'm just rounding later. So what we've got here is 19 meters per second. 19 meters per second. There's our answer. I know it says N over X, but you get the idea. Let's see what answer they got to see if we came close. Yeah, look at that. We got the same answer. Okay, so I think that's the last one, and then I think at this point I'm going to have you go ahead and do some problems from the book. But let me bring this back to the top for your notes, okay? This is page 166, example 5. I'm going to put it here so you can see the top. If you need to take some notes there, you can pause it if you need it. Now I'm going to move it. Now that you're done pausing it, I'm going to move it up so you can see everything. I guess you can pretty much see everything anyway. So just to review, the whole story is really about work equals kinetic energy final minus kinetic energy initial. And work is force times the component of the distance that is in the same direction as the force. I mean, the component of the force that's in the same direction as the distance moved. So it's weird here because I know I said F cosine theta, and here we have an F sine theta. So you really have to look at things to figure out how to find that component. Because we've got our mg coming down, and this is our 25 degrees right in here. So the opposite, which means the sine multiplied by the hypotenuse, the mg, is going to give you the force that is in the direction we want, the component of the force that's going downhill. This other component of the force, that's just pushing the skier into the snow. And of course, there's a normal force going back up, right, coming out of the snow that pushes the skier upward. And that one is balanced by this one here. So you've got the normal force here and here. You've got the mg cosine theta going there. And then, of course, we also have that friction force going backwards if you want to have a true free body diagram of everything that's going on. But the friction force is apparently smaller than the x component of the gravity, of the weight. Otherwise, the skier wouldn't be moving downhill and actually accelerating downhill, right? Because the frictional force is 174 newtons, and the force that comes from taking that sine, no, that's 170. This is actually, this piece here is the piece that comes from gravity, the 580 sine 25. The 71 is the friction. So the question of what this 580 sine 25 is, I don't remember. I don't know if I ever came up with it. But whatever it is, that must be bigger than 71, because when you subtract them, you get a positive 174. So this is, that means that this is 103. Is that right? No, 100, like 245, I think, because you subtract 71 from it and you get 174. Well, that's enough. Hopefully you got an idea of the work energy theorem. Let me see if I can go back to it in the very beginning. Okay, here it is, the work energy theorem right here. Work equals kinetic energy final minus kinetic energy initial. That's what this whole lesson is about. If you wanted, you can do all these kind of problems because you can calculate the work, and if, for instance, you know the kinetic energy you start with, and you know the mass, you can find the final velocity from finding the kinetic energy final, because each kinetic energy is just 1/2 mass times velocity squared. So that's it for now. I will, hopefully I'll give you some problems to do next. Let's see. I always hit the wrong one there. This is the one.